Our visual system covers more than 135 degrees vertically and 160 degrees horizontally, but we perceive detail only within about 5 degrees around the direction we're looking. This tiny portion of the visual field projects onto the retinal region called the fovea. Acuity then falls off rapidly with the angular distance away from the central gaze direction. Our system exploits foveation on existing graphics hardware by rendering to 3 nested render targets, or eccentricity layers, centered around the current gaze point. Commodity eye tracking hardware tracks the user's current gaze position, about which the eccentricity layers, highlighted here in gray, are centered. The central layer matches the sampling rate of the display. The next layer out is sampled at half the display's resolution in each dimension. Finally, the full screen background has roughly 1/25 as many pixels as the display. These layers are then composited together smoothly to avoid creating any artifacts which might catch the eye. With a reduced sampling rate in the periphery, strong temporal and spatial aliasing artifacts degrade the apparent quality to unacceptable levels. We use a combination of traditional multi-sampling, jittering the pixel sample positions, and reprojection blur. The aggregate effect provides efficient yet highly effective anti-aliasing. Exactly how acuity falls off with eccentricity is a well-studied problem in the psychophysical research literature. We base our system on these results, but there is a complex and uncertain trade-off between blurring and aliasing in the periphery. Finding the optimal balance has received less scientific attention and probably varies over different people and different types of visual content. This makes it important to tune how aggressively the system degrades peripheral sampling in favor of performance. To do this tuning, we collapse the parameter space of the system to a one-dimensional quality slider. For any setting of the slider, we assume a linear model for how minimum angle of resolution increases with eccentricity. We then adjust the model's slope. A steeper slope offers more performance savings, but may be perceptibly blurry in the periphery to some people. A shallower slope is more likely to be perceived as identical to non-foveated rendering, but at reduced savings. We conducted user studies to investigate this 1D quality space. For our first test, we sought the highest performance setting which was perceived as equivalent to conventional 3D rendering. We chose a fly-through of a simple landscape populated by common objects. The subject was shown a few seconds of both standard rendering and a foveated rendering at some point on the quality slider, in pseudo-random order. The subject was then asked to choose whether the first was better, the second was better, or they were the same.
Seems about the same. Okay. Ready?
In the second test, foveation quality was gradually changed between our reference high-quality setting and a variable high-performance setting. As in the previous test, we pseudo-randomized whether the reference rendering came first or second, as well as the order of higher performance settings. The objective here was to find the highest performance setting perceived equivalent to a high-quality setting. The combined tests show that substantial savings may be realized without degrading quality, and even greater speedups if we allow visible but acceptable blurring in the periphery. We measure a factor of 5 to 6 speedup with our current system. The convergence of high display resolutions and commodity eye tracking, along with growing demand for lighter weight and lower power graphics hardware, will make foveated rendering even more attractive in future platforms.